Hi, I'm Antonio Sala, and in this video we are going to discuss the closed loop equations and the stability analysis of a double integrator system. In plain terms, a moving mass in which my manipulated variable is the force exerted onto it. So in this video we'll discuss theoretical analysis on the closed loop control of that system, and for brevity we'll discuss the closed loop equations and stability analysis under proportional and proportional derivative control, and final value steady state error, as well as integral action, will be left for subsequent videos. So mass times acceleration s squared position in Laplace domain equals force. So transfer function is this one, 2 over s squared for my half a kilogram mass, and with some technology I can compensate the friction and act with electromagnetic, hydraulic or whatever technology to move my mass. If my desired movement is 1 meter and my maximum force is 1 Newton, then with the uniformly accelerated motion we will not able to achieve that in less than 1 second. Just, to get an intuition on how fast we should act. In prior videos, by trial and error, we introduced the transfer function into a PID simulator application. Here we have it. And we saw that under proportional control there were sustained oscillations, and the higher the gain, the higher the frequencies, but they were not damped. And if I added some derivative action, then damping increased more and more. Of course, saturation and measurement noise need extra care because there is a lot of difference. But in this video we will try to analyze the theory behind this behavior of proportional and proportional derivative actions, and in particular the stability, settling time, damping, and the like. So let's go. If we recall the heuristics on what the meaning of proportional and derivative actions are, proportional actions were sort of a virtual software-based spring that exerted a force proportional to the distance between the actual position of my mass and that of the set point, reference value, 1 in this case. So this virtual spring is the proportional action, and then the derivative action was a virtual damping, let's say. And we had two options. First option was damping by exerting a force proportional to the speed of the mass. That would be, sort of friction with the rolling surface. And second option would be damping with a force proportional to the time derivative of the error, time derivative of the relative distance between the mass and the set point. And well, that would end up being equivalent to a software realization of this damper here. And we also could have intermediate options. But okay, for simplicity, in this video we will just discuss this option at the top right of the derivative action, derivative of the error, in order to compute the closed loop equations. Treatment with the other friction option is similar, but for brevity will not be discussed in here. Of course, the advantage with respect to mechanical, let's say, suspension tuning of springs and dampers is that if I do it by software, then changing the damping and spring characteristics can be done just by typing on my keyboard, and I don't need to dismantle my car to change the suspension. But of course, it requires, software sensing filtering technology that somehow has a greater complication than a passive suspension, let's say. But okay, let's now go into the computation of the closed loop equations. So if we recall the closed loop block diagram, we will analyze this situation in which my process will be, of course, 1 over s squared. And there we have a sensor with some measurement noise that will provide the measurement of the position y control variable to be compared with a set point reference value, and some error will be computed, subtracting them, and my controller will react to that error. And the transfer function of my controller will be for a proportional derivative controller in the form kc times 1 plus TDS. This is the one we are simulating in this application, but in our theoretical developments, we will just remove parentheses, and then the term that multiplies S, the derivative action, we will call it KD. And the Kc constant, well, will be renamed to Kp to denote the proportional term and the derivative term. Of course, the cyan and pink representations are 100% equivalent, so we can choose one of them just for convenience, so depending on the textbook or the control software you are analyzing, you may find one of those two expressions, but you can interchange between them at will, and then we will use the pink one in our equations for convenience. Good. So let us compute the closed-loop equations. First, in a generic point of view, this is the controller equation. This is the process equation, in which the input is my manipulated 1u plus some du disturbance, and then the measured error is the difference between R and the measured output, y plus noise. So I have three equations, three unknowns, u, y, e, and then solving for them and putting them in pretty form, we can have this expression, for instance, for the output, which is what my user will see, how the position of my mass moves. But even if he doesn't know, he actually wishes the error signal, this thing here, to be small, or if it is initially at the start of my maneuver, my user wishes this error to get small quickly in a short time period. So for our theoretical computations, we will use this expression for the error and we'll analyze its properties. So the only remaining thing is, replacing G and K by my double integrator plant and my proportional derivative controller, respectively. So let's do it. I've just copied the error expression from MATLAB, and then if I replace G and K, I will get E of S equal to 1 over 2 over S squared, my process, times K proportional plus K derivative times S plus 1 times set point plus something multiply the disturbance, the denominator exactly the same, so I just copy it, and numerator G 2 over S squared, and I will not write the equations regarding the measurement noise because, well, usually measurement noise, if my sensor is good, should be a small thing, and also this transfer function that multiplies to n will be exactly the same as that multiplies R. So whatever we can say about the properties of this piece will be identical with respect to measurement noise, and okay, we assume that measurement noise n will be much smaller than set point value, 2%, something like that. So this is it. Then this is the error, and now we just need to put it in pretty form, by removing denominators, let's say. So if I multiply up and down the fractions times S squared, I will get this thing for the set point and 2 here and same denominator. So this is the disturbance response. So these are the closed loop equations with small measurement noise, let's say. And then the first thing we should analyze is stability. So stability means analyzing the roots of the characteristic equation, which means making denominators of the transfer functions equal to 0, so this thing equal to 0 gives me the closed loop poles, the exponentials of the time response. Then we will first analyze the proportional control only. So if KD is 0, characteristic equation is s squared plus 2kp equal to 0, which has roots, this thing. And then, okay, if kp is positive, then this thing will be imaginary. And if kp is negative, then I will have a positive root and a negative root. So I will have a positive exponential, so this will be unstable. I mean, in my intuition on the proportional control, this is a spring that if it is a normal spring, then it will have oscillations. And if there is no damping, they will last forever. That would be the positive k, the imaginary roots. And if this software spring exerts force in the wrong direction, in the sense that, okay, the further left the mass is, the higher the leftwards force is made, then of course that will quickly exponentially explode to infinite distance. And that is what we are discussing here. I mean, kp negative is nonsense from an intuition point of view. It will have exponential instability, and if we set kp to a positive number, then this will be the square root of negative, so the poles will be plus minus some beta, let's say, times the imaginary unit that I name j, and these imaginary poles correspond to persistent non-damped oscillations, and that is what we saw in our simulations of proportional control, these persistent oscillations, and its frequency was proportional to the square root of the gain, in the sense that with gain equal to 5, I get like 3 periods in 6 seconds, and if I multiply that by 4, I put 20, then I get 1, 2, 3, 4, 5, 6 periods in 6 seconds. Indeed, the frequency of the oscillations, beta in radians per second, is proportional to the square root of the proportional gain. So this is the theoretical justification of the behavior we saw with proportional control in simulation. This is a marginally unstable loop. Persistent oscillations that never reach set point is useless for most control purposes, so we call it marginally unstable, let's say. Other people call it marginally stable. It's just a name, but it's usually the sign of a non-working controller. And of course, if kp were negative, this would be exponentially unstable. So this is the analysis of proportional control. Then let's analyze now the full proportional derivative control. So the closed loop poles will be computed with standard, secondary school formula, minus this thing divided by 2, minus kd, plus minus square root of 2kd squared minus 8kp divided by 2, and then putting 2 as 2 squared inside the square root, so it enters as 4. This thing is equal to minus kd plus minus square root of kd squared minus 2kp. So these are the closed loop poles with proportional derivative control. And then if we assume kp positive, so this analogy is a normal spring, pushing towards the set point, which is the right thing to do, then we have several situations depending on whether the sign inside this square root is positive or negative. In particular, if we have a small kd and kd squared is less than 2kp, then we will have the square root of a negative number, so the closed loop poles will be S equal minus KD, real part, plus minus something imaginary. Then it will be stable if the real part of the poles is negative, so this will stable if KD is also positive, and it will be oscillatory. So if derivative action is small, I will have oscillations. Indeed, if we simulate, this was only proportional, and then if I add a little bit of derivative action, well, we have oscillations that are stable, they get ultimately damped and disappear, but, well, here we have an oscillatory behavior, and the real part of the poles is KD, so the oscillations decay faster if I increase this KD or TD. Recall that we are using another parameterization, but it's just for convenience, the equivalent, so, well, the larger KD or TD is, the faster the damping is, until, well, there will be some point in which, if this happens, the thing in the square root will be a real thing, so we'll have a non-oscillatory behavior, and, well, if Kp is small, then the square root of KD squared will be KD, but then the thing inside the square root will always be lower than KD, so I will have some minus KD plus minus something smaller than KD, so I will have two negative real poles, so this will be stable. Okay, so basically for positive KD and positive Kp, this thing will be stable in both cases, and there will be one value of derivative action that will make this thing non-oscillatory. For instance, let us imagine that Kp is 2, then the transition between oscillating and non-oscillatory behavior will happen at Kd equal 2. In this case, my poles will start to be real. Let us try it in simulation, but okay, as I used this parameterization, Kc1 plus Tds, then this means that if this is 2 and this is 2, this must be 2 and this must be 1. So let us plug that in my simulator, 2 here and 1 here, and, well, here we have a non-oscillatory transient, and if my derivative action is lowered, oscillations appear. Of course, at start they are extremely damped, so they are barely noticeable, and they are non-existent here, and of course putting no derivative filter will be the exact response predicted by my theory, so no oscillations, and with stronger derivative action I will have two real poles. Note that there is still a bit of overshoot, because apart from the poles of the transfer functions, we have some zeros. Then I can go to one side of the set point and go back, but this is a non-oscillatory overshoot in the sense that it will never cross the set point line again down, but oscillatory overshoots continuously cross up and down. Then we will conclude with this. In this video, we explored how closed-loop equations for a proportional derivative control were computed, and we explored the stability, analyzing the roots of the characteristic equation. We discovered that with strictly positive proportional and derivative gains, the loop was stable, and if derivative gain was low, we had oscillations that took a long time to disappear, and if the derivative gain was high, we had real poles, non-oscillatory, stable, transient. However, what we did not discuss is the effect of saturation and measurement noise, and the obliged presence of a noise filter to filter that high frequency noise. That makes the response to be very different to the theoretical prediction if my gains are high. So actual control need to limit my gains to avoid excessive high frequency measurement noise amplification and excessive amplitude of the control. With something like this, let's say, theory, linear in science, and practice are closer. So one thing is doing mathematical manipulations on this formula. Another thing is choosing which closed-loop specifications are sensible ones so that what I compute in theory about stability and settling time and the like gets reasonably reflected in practice. So with this stability analysis of my proportional derivative controllers under ideal non-noise, non-saturating situations, we finish the video here. Thanks for watching.